This contraption is a variant of an ornithopter. It is designed around concepts taken from a helicopter and applied to an oscillating wing. Its flight performance reveals as much. This contraption uses hydraulics to rapidly change the pitch angle of the wings. That is, the wings are actively twisted and don't depend on aerodynamics to determine their angle. Since these wings are going to be treated as oscillating helicopter blades, it's essential to consider the effect of vertical blade flapping, and therefore the elasticity in said axis of motion. Consider the case of rigid articulation. The wing cannot move up and down, it can only oscillate and change pitch angle. Under these conditions, we can generate lift by reversing the angle of attack of the wing at the end of each stroke. However, we do so by rotating the wing by an acute angle, such that the leading edge of the wing reverses with each stroke. As a result, the pitch hydraulics only have to oscillate the wing by a relatively small angle. Since the wing can't flap vertically, it's constrained to oscillate about the flapping plane. The dynamics change once we allow the wings to move vertically. Consider the case of damped elastic vertical motion. The vertical elasticity is such that an initial disturbance decays without rebound. Here the wings begin to move in a very slight figure-8 pattern. They also begin to deflect in the direction of the lift force. Beyond that, the motion of the wing is smooth with very little vertical deflection. Next, consider vertical deflection with an underdamped spring. An initial disturbance creates an oscillatory motion that takes a long time to settle. The end result is that the wing path takes a very pronounced figure-8 shape. There is large vertical displacement of the wing when it flaps back and forth. This displacement alters the angle of attack of the wing. The most pronounced difference appears to occur at the middle of each stroke. To control this machine about the yaw axis, we can apply asymmetric drag by tilting the wings in opposite directions akin to ailerons. To control thrust, we can change the angle of attack of the wings as they oscillate. For low thrust, we simply increase the angle of attack by a very small amount, and it reverses at the end of each stroke. To increase the lift, we simply change the amplitude of this oscillation, such that the wing sees a large angle of attack at the middle of each stroke. These deflections are directly analogous to collective pitch in a rotary wing. Notice how the figure-8 pattern becomes more pronounced as the lift increases. To control roll, we can simply make the collective asymmetric. The net angle of attack of a wing is increased on one side and decreased on the other. Due to the deflections of the springs, this induces a large torque about the fuselage. The asymmetric collective is clearly illustrated in slow motion. Pitch control can be obtained by modulating the changes in angle of attack. In this case, we increase the lift near the front of the aircraft and decrease it near the rear of the aircraft. Since the wing changes leading edge at the end of each stroke, the aforementioned modulation has to change direction as well. Consequently, the pitch modulation occurs at twice the frequency of the base oscillation. Moreover, the torque generated by these pitch modulations depends on the amplitude of the wing flapping. A larger amplitude increases the moment arm that the lift variations have to rotate the fuselage. Therefore, this control mechanism is only efficient for large amplitudes. Small amplitudes don't allow the wings to move forward and back enough to generate a significant moment arm. The elasticity and amplitude of the wing also affect the stability of the aircraft. For rigid flapping, the stability is asymmetric. Any velocity about the pitch axis causes the aircraft to pitch into the velocity, meaning it becomes unstable. The roll axis behaves in the opposite manner. Lateral velocity causes it to remain mostly the same or even deflect opposite the direction of the motion, such that the thrust from the wings decreases the velocity. When we increase the amplitude of the wings, the stability remains the same. Pitch is unstable and roll is neutral to positively stable. The performance changes drastically once we allow the wings to flap vertically with a damped elastic spring. At low amplitudes, the pitch axis remains unstable. The aircraft rotates into the direction of motion. The roll axis remains stable, but nonetheless the uprighting tendency is much stronger. When we increase the amplitude, the pitch axis becomes stable. It generates a significant torque that rotates the aircraft to oppose any displacement. The roll axis remains stable and also opposes displacement. Therefore, as a whole, the entire aircraft is mostly stable. While the aircraft may have a degree of natural passive stability, this is nonetheless augmented by using a PID controller to self-upright the machine. The controls are sufficiently powerful enough to do this effectively and consistently. It is this large amplitude configuration that we have used to make a controllable platform, as it possesses positive stability and large control moments about the pitch axis. Once in flight, this aircraft flies very similar to a helicopter. You can bank the aircraft in any direction to fly in that direction, and you let go of the controls to have it self-upright. Compared to an ornithopter with passively twisted wings, this machine experiences less drag, so it can translate at higher airspeeds. It also has much larger roll stability. The PID controller is not being forced to keep the aircraft stable when it's translating. The motion of the fuselage is also smooth. This is especially noticeable in a first-person view. The aircraft flies smoothly with no noticeable loss of control or stability. The pitch axis feels much the same. In a first-person view, when the aircraft is banked forward, it's very noticeable that it can gain much more speed compared to a passively actuated wing. Once the aircraft has gained airspeed, if we raise the nose, the aircraft gains height as it decelerates. This indicates much lower drag, as the kinetic energy of the aircraft is transformed into potential energy. Despite the wings operating at low angles of attack, where the drag is low, the yaw control is still quite effective and can rotate the aircraft quickly. The aircraft is essentially a helicopter with oscillating blades. Even with the improved high-speed performance, the low-speed performance is just as good. The machine can hover with great control and plenty of stability.